Curve C has this equation, and we're asked to find dy by dx, and then the second derivative. So the first thing I'm going to do is write it all in terms of powers. So x squared minus 2x minus 24x to the half. Now I'm ready to use our rule from year 1, d by dx of x to the n. Bring the power down, reduce the power by 1. You can show that using first principles, but it's a rule to just learn and use. So we're going to get 2x minus 2. That's kind of a special case. It still works, by the way, this rule, but it's better to just remember that the 2x becomes 2 because it's basically the gradient of y equals 2x, which is 2. If you think back to y equals mx plus c, then it's going to be minus 12x to the minus a half. Second derivative, 2, and then I'm doing minus 12 times minus a half. That's going to become plus 6x to the minus 3 over 2. So there we have it. Verify that C has a stationary point when x is equal to 4. So what we don't have to do here is set it equal to 0. We just need to show that it's equal to 0. You could try and solve it, except the x to the minus a half is going to make it quite complicated. So I'm going to avoid that completely. When x equals 4, dy by dx will equal 8 minus 2 minus 12 over, that's going to be the square root of 4. So that's 6 minus 6 actually, because the square root of 4 is 2, which gives 0. And therefore, C has a stationary point at x equals 4. Okay, don't need to do anything else. Except part C, we need to determine the nature of it. So for that, we can use the second derivative. We've already got it from before, so we can just sub in x equals 4 into that. So when x equals 4, okay, this time it's actually 1 over the square root of 4 cubed. By all means, use your calculator for that. Just do 4 to the power minus 3 over 2. But it's going to be 6. I mean, it's definitely going to be positive. 2 plus 6 over, it's going to be 8 actually, square root of 2 times 3. So 2 and 3/4 or 2.75. Now, this is greater than 0. That's the main thing. Therefore, the stationary point is a minimum. Okay, and just a little explanation why the second derivative being 0 leads to that. So if we look at the minimum, here we go. Here's a gradient of 0 momentarily. Now, if we look just to the left, we can actually see that the gradient is negative, but it's actually increasing. It's getting less negative. Then afterwards, it continues to become more positive. So the gradient itself is increasing, which is why that means a minimum. Okay, if the second derivative is greater than 0, it means the gradient is increasing at that point, as opposed to a maximum where the gradient's actually, well, it was positive, it becomes negative, it's actually decreasing. Um, Stationary points are a little bit different. Again, remember we can't, sorry, not stationary points, points of inflection, because we can't use the second derivative of that one. It's positive, then 0, then positive. So you need a different method for it. But I'm just trying to explain why this leads to a minimum. Anyway, this is the question done. Well done.